The backbone of efficient computing, mastering data structures in algorithm design in the ever-evolving world of computer science, data structures form the foundation upon which efficient algorithms are built. From simple arrays to complex graphs, these constructs determine how data is stored, accessed, and manipulated within programs. Understanding data structures is essential for any programmer aiming to optimize performance and solve real-world problems effectively. This guide dives deep into their significance, types, applications, and best practices. What are data structures? Data structures define ways to organize and store data so that operations can be performed efficiently. They provide a means to manage large amounts of information systematically. Different data structures excel at different tasks depending on what kind of access patterns or transformations are required by an application's logic. Primitive versus non-primitive. Primitive structures include basic types like integers and characters, while non-primitive ones encompass arrays, lists, trees, etc. Static versus dynamic. Static structures have fixed sizes determined during declaration, whereas dynamic ones adjust size as elements are added or removed dynamically. Choosing between various data structure implementations often depends heavily on factors such as memory constraints, speed requirements, ease of use considerations, and scalability needs across different problem domains. Fundamental types of data structures. There exist numerous fundamental categories of data structures, each designed specifically for particular purposes, ranging from fast lookups to hierarchical organization. These foundational structures serve as building blocks, enabling developers to construct more sophisticated solutions tailored towards solving intricate computational challenges. Linear structures include arrays, linked lists, stacks, queues where elements follow sequential order either contiguously or through pointers. Nonlinear structures, such as trees and graphs, allow branching relationships among items, facilitating representation of complex relational models. Each type has its own set of advantages, making them suitable under certain conditions. Understanding when and why they're used becomes critical skill set for proficient coding. Arrays. The cornerstone of memory management. Arrays represent collections of homogeneous elements arranged consecutively in memory, allowing direct indexed access via numerical positions known as indices. This arrangement enables constant time complexity O(1) for both retrieval and modification operations, provided we know exact location ahead of time. Advantages. Fast random access due to contiguous storage layout simplifies implementation significantly, especially when dealing with primitive data types. Disadvantages. Fixed size limitation forces pre-allocation, potentially leading waste space issues unless managed carefully using techniques like resizing strategies. Despite limitations, related flexibility regarding capacity adjustments. Arrays remain widely utilized because their simplicity aligns well with many common scenarios requiring rapid lookup capabilities without overhead associated with other alternatives. Linked lists. Flexibility through pointers. Unlike arrays whose elements occupy adjacent locations in RAM, linked list nodes contain references pointing towards subsequent entries, forming chains instead of blocks. This architecture provides greater adaptability since inserting new items doesn't require shifting entire segments, unlike array-based approaches where expansion might necessitate copying existing contents elsewhere first. Singly linked list. Each node points exclusively forward, creating linear progression useful mainly for traversal purposes rather than bidirectional navigation. Doubly linked list. Nodes maintain connections backwards too, offering two-way movement, beneficial situations demanding frequent insertions/deletions near ends. However, increased pointer usage introduces additional memory consumption compared to compact representations offered by traditional flat structures, but compensates by eliminating need for upfront allocation decisions entirely. Stacks and queues. Principles behind last-in first-out operations. Both stacks and queues implement LIFO, last-in first-out, principles, though differing slightly based on ordering semantics employed internally. A stack operates similar manner telephone directory, wherein latest call gets answered first, maintaining strict hierarchy dictated solely by insertion sequence itself. Applications. Stacks find utility, particularly recursion handling, function calls, execution, context tracking, undo mechanisms, text editors, implementing backspace features. Operations. Primary functions involve pushing onto top, removing from same end, checking current state without modifying underlying collection. Queues contrast sharply, functioning akin ticket lines, ensuring fair distribution resources amongst waiting entities following FIFO, first in first out, rule guaranteeing consistent service delivery pattern regardless arrival times. They prove indispensable managing print jobs, scheduling processes, network packet transmission, routing protocols, wherever orderly processing imperative over immediate response prioritization. Trees. Hierarchical organization of information trees model relationships hierarchically representing parent-child linkages, abstractly yet concretely applicable diverse fields, including file systems, organizational charts, XML documents, databases. Rooted at single starting node, branches extend downwards forming substructures until reaching terminal leaf nodes containing actual values being processed through tree traversals. Binary trees. Restrict each position holding maximum 2 offspring left-right respectively, aiding binary search implementations, sorting algorithms, heap management. AVL trees. Self-balancing variants ensure logarithmic height, preventing worst-case degeneracy, typical unbalanced cases, thus preserving optimal operation speeds consistently. Efficient querying, updating, deletion become feasible thanks structured layouts, reducing ambiguity, inherent unordered aggregates, thereby enhancing overall system responsiveness, notably impacting performance-critical software components. Graphs. Modeling complex relationships and networks. Graph theory provides powerful framework capturing multifaceted interconnections present social networks, transportation infrastructures, biological pathways, cryptographic schemes. Vertices. Connected edges create versatile blueprints, adaptable, countless contexts, varying degrees complexity, represented edge weights, directional nature, presence, absence, loops, multiple links. Directed acyclic graphs. DAG. Useful dependency resolution, project management, task sequencing, avoiding cycles causing infinite regressions, paradoxes. Weighted edges. Allow quantification, distances, costs, capacities, crucial pathfinding, shortest route determination, resource optimization, logistics planning. Algorithms leveraging graph properties, range, breadth, depth searches, minimum spanning tree constructions, maximum flow computations, identifying strongly weakly connected components, analyzing communities, emerging datasets, revealing hidden patterns, previously undetectable conventional methods alone. Hash tables. Rapid lookup with collision resolution strategies. Hash tables utilize hash functions, mapping keys uniformly distributed buckets, minimizing collisions probability, maximizing cache locality, improving average case performances substantially. Collision occurs whenever distinct inputs produce identical output hashes, necessitating secondary measures, resolve conflicts, maintaining integrity, correctness, results returned, queries executed against table. Open addressing. Resolves clashes, probing nearby slots sequentially until empty found, ensuring minimal displacement from original index computed initially. Chaining. Links colliding records together via auxiliary data structures, typically linked lists, permitting flexible growth, accommodating variable load factors gracefully. Optimal design balancing. Trade-offs between computation expense, storage efficiency remain central concern, influencing choice methodologies, deployed production environments, subjected high throughput demands, stringent latency constraints. Heaps. Prioritizing elements for efficient extraction. Heaps maintain partially ordered sequences, enforcing min/max heap property, where root contains smallest/largest element, respectively accessible instantly, fulfilling priority queue requirements succinctly. Insertion deletion maintains structural consistency, automatically adjusting internal configuration, reheapifying upwards downwards, accordingly preserving invariant characteristics throughout modifications applied dataset. Minheap ensures every child node holds value greater than parent, supporting extraction minimums, quickly advantageous. Dijkstra's algorithm greedy approaches, selecting next closest vertex efficiently. Max heap. Opposite behavior prioritizes maximal elements for most ideal circumstances, needing instant identification, highest valued item available, pool selections. Such functionality proves vital. Operating systems job schedulers event-driven simulations whenever timely processing events contingent upon relative urgency importance assigned individual components involved workflows executing concurrently asynchronously. Conclusion data structures form the backbone of modern computing, enabling efficient manipulation of data in algorithms and programs. Mastery of these structures allows programmers to build scalable, performance solutions tailored to specific problem domains. Whether working on optimizing search engines, developing game engines, or designing complex financial systems, choosing the right data structure is paramount. Continuously expanding your knowledge of advanced topics ensures you stay competitive in today's rapidly evolving tech landscape.